Hello everybody, welcome to our today's webinar on the 20th of November at 3 p.m. European time. Probably most of you not from Europe, but we're happy that we all can come together through this online tool. And our today's topic is scientific background of physical information medicine. We have today our speaker, our Master of Science, Mr. Jan Senekowitsch. Before I tell some details of his vita, I want to give you some technical instructions. First of all, you can see us. We cannot see you, but you can communicate with us during the chat. So we're going to start with the presentation of Mr. Jan Senekowitsch. And after the presentation, we open a chat room and you can ask any questions that you like, and we will going to answer them live. If you have any technical problems, you can contact us. If you cannot contact us through the chat, you can contact us at info@Mag.rer.nat.Jan. So this webinar is hosted from the company Mag.rer. I'm your speaker today. Well, I'm your moderator. Your speaker is Mr. Jan Senekowitsch, who is a Master of Science, and he did a study of theoretical physics at the Karl Franzens University of Graz. Graz is in Austria. And his diploma thesis was at the Institute for Physical and Theoretical Chemistry in the university. As well, he attended the Institute for Physical and Theoretical Chemistry, also in Graz, for cluster calculations within the framework of few particle relativistics quantum mechanics. And on top, he also was a tutor in laboratory exercises. Mr. Senekowitsch, I'm very excited to give you the word and to start with your presentation.
Thank you. I hope everybody can see the presentation.
It looks good. I think you can start.
Okay. Welcome to the webinar with the topic Scientific Background of Physical Information Medicine. I've divided it in 4 parts. First, I'm going to talk about basic physical concepts, which are necessary to understand the measurement methods in energetic medicine or informational medicine. Then I'm talking about dissipative structures, which are models for organisms and non-thermodynamic equilibriums. Then I'm discussing bioenergetic medicine and its measurement methods. First, what's biophysics? Biophysics is derived from the classical Greek word bios and physic, meaning life and natural research. In biophysics, we try to apply concepts and methods of physics to study biological phenomena. We draw from the main principles of thermodynamics, electrodynamics, quantum mechanics, and classical mechanics. And the goal of biophysics is to describe processes within the biological systems on a molecular and supramolecular level, respectively. First, I'll talk about basic physical concepts, which, because maybe not everybody is familiar with them, I quote Mark Twain with get your facts first, then you can distort them as you please. First, I'll address matter. The composition of matter is described by the Standard Model in modern physics. The constituents of matter itself, the smallest particles, elementary particles, are the quarks, leptons, and gauge bosons. On the right, you can see the scale of the particles. So the smallest are the quarks, which are the building blocks of the hadrons. Hadrons are the nuclei, the core particle of the atom, like for example proton and neutron. Then leptons, for instance electron and neutrino, and gauge bosons, which bosons, if you're not familiar with it, the aforementioned hadrons and leptons are fermions, and the bosons are insofar different as they have a different spin. It's more of a detail at this level, but hadrons and leptons have half integer spins, and gauge bosons have an even spin, so 1 to 0. Therefore, fundamental interactions between these elementary particles, and these are conveyed by the aforementioned gauge bosons. These are the gluons, gravitons, V and Z bosons, and photons. Gravitons are still hypothetical, but it's current research done on it, quantum gravitation. On the right side, on this depiction, we see the relative strength of these interactions relative to the gravitation with relative strength 1. And we can see that weak, strong, and electromagnetic force are by far greater than the gravitation. Like, for example, the weak force is about 10 to the 25th, strong force 10 to the 38th, electromagnetic force 10 to the 36th. On the far right, we see in this depiction the range of these interactions. Although the strong interaction is the strongest known interaction, it has also a very limited range. Both weak and strong interaction are mostly confined to the core of the atom, to the nuclei. And electromagnetic and gravitational force both infinite range. I must mention that the electromagnetic force, although it's much larger than the gravitational force, cancels out because of the almost neutrality on a larger scale of the universe. So on a large scale, gravitation, although it's very small in force, relative strength is the dominating force. All of currently observable phenomena can be described by one on the combination of these interactions. Now I'll talk about energy. Energy is a conserved quantity in a closed system, meaning it cannot neither be created from nothing nor vanish in a closed system. In an open system, meaning a closed system is if you imagine a certain space and there's no interaction leaving this space or coming into this space, then all energy within is conserved. This can be, for example, the universe or an experiment. It depends on the mostly it's used as an approximation. So you can approximately describe something as a closed system. If you're interested in the interaction of a system with its environment, you can describe it as an open system, and energy decreases in these systems to the extent of how much heat is given the system gives off if it performs work or emits radiation. So you have a transfer of energy or mass from the system to the outside. Energy can be available in different forms, which can be converted into each other. although not without losses. Losses meaning the different types of energy which are not converted in not converted in the desired energy. Mostly it's heat. This relates to the perpetuum mobile of the second kind, meaning in the perpetuum mobile of the first kind says it's not impossible to create energy from nothing. The perpetuum mobile of the second kind says you cannot convert energy in a certain energy type without having some kind of loss in form from heat. Examples for types of energy are potential, kinetic, electrical, chemical, and thermal energy. Thermal energy is a little bit outdated, maybe a bit because thermal energy is kinetic energy, but it's still used as a macroscopic way of talking about energy. Because kinetic energy at the molecular level is sometimes not used for describing processes. Energy is closely related to work. Work is the change in energy of a system involving a process. I want to insert here the concept of a conservative field, which I will talk in detail a little bit later. But for the sake of work in a field like gravity field or the electrical field, there's a concept of a conservative field. There's no rotation in this field. This means work depends only on the starting and end point of some movement, for example. Like lifting up a weight does not depend on the exact path, but only on the height about the Earth, for example. A different example is work in an electrical field, where the displacement of a point charge against the direction of the field needs energy to move the particle, but increases the potential energy of the point charge, similar to the lifting of a mass in a gravitational field. And vice versa, displacement of a point charge in the direction of the field increases the kinetic energy of the point charge at the cost of potential energy, similar to dropping a mass in a gravitational field. Electrical energy is stored in the electrical field and can be measured macroscopic as amperage E and voltage U. Now I'll discuss scalar and vector fields. Generally speaking, the definition of a field is the spatial distribution of a physical quantity, which can be either scalar, scalar meaning just a ticket, like for example a temperature distribution or the gravitational potential or electrostatic potential, or vectorial. Vectorial fields are the gravity field, electrical field. The difference between the electrostatic potential and electrical field is, I forgot to mention it earlier, that in a conservative field, it's possible to define the force, meaning the direction of the field lines, as the negative gradient of the potential. So the potential differentiated in all directions gives the electrical field. We see on the left at the bottom a scalar example for the scalar field. It's the gravitational potential of the Earth. The red circles are the equipotential surfaces. What I said earlier about the gradient means in the highest in the direction of the highest change, meaning the blue arrows pointing at the Earth are this is the utmost change, this is the field lines of the gravity field. On the right, you see a little bit more complicated field. It's a superposed field of the Moon and Earth. Here we see that the arrows pointing at the centers of mass. These are it can be imagined that these arrows, if you would let a small mass loose, it would follow at some point in this field. It would follow the arrows of this vector field. Vector means it's not just a digit; it has a direction at every point in this field. That's the important difference between scalar fields and vectorial fields. And now the electrical field, it's more like the gravitational gravity field, with some differences, because it's governed by a very similar force, the Coulomb force, but it has two charges. Whereas in gravity we only have mass, and it's only attractive. In the electrical fields we have plus and minus charge. Plus minus charge attracts, and the same charges repel each other. At the bottom we have depictions of these circumstances. So and it's just convention, but it's usually in the technical direction of fields. The point charge which follows these lines is positive. So it has historically reasons, more or less, because physicists didn't know if the electron was negative or positive. So it shows some direction. It's called the technical current direction. So actually, electrons would move against the field lines. Yeah. Closely related to the electrical field, we have the magnetic field. This connection is not trivial. It's explained by the Maxwell equations, which explain the connection more closely. There are some difference with magnetic and electrical phenomena, as insofar as there are no magnetic monopoles. The magnets also always come with two poles in north-south poles. If we look at the bottom, we see the depictions of magnetic fields. For example, we can imagine that there's small compass needles between the magnets, which always align with the field lines of the magnetic field, much like on the Earth we use compasses for navigation. It's the same thing. Yeah, electrical charges, for example, would experience different deflections in magnetic fields. These are governed by the Lorentz force. An electron moving along a field line would deviate in a circular motion perpendicular to the field line. So this is a more difficult deflection. There's still one phenomena which, for example, emerges in electromagnetic waves. This is alternating electrical fields and alternating magnetic fields. cause vortex fields of the for example, what I'm trying to say here is magnetic alternating fields, because depending on the field strength, electrical vortex fields, alternating electrical fields produce magnetic vortex fields. This means if for example, the human body is in a magnetic field, depending on the field strength and how much it's alternating, exists within the body are produced vortex fields, and also there's a naturally occurring currents in the body, like ions in the bloodstream or the nerve stimuli, and this produce magnetic fields. So there's a natural electrical and magnetic field of the body. Physical oscillations, very important phenomena in physics, and I'll discuss some of the properties of physical oscillations. Why they're important here in this context. For example, the heart rate is also an oscillation. Frequency, for example, is defined as events per second. 1 Hertz is 1 event per second. The heart rate is about 60 Hertz. Wavelength is the distance from peak to peak. For example, if you look at the electrocardiogram to the right, on the right depiction, we can see the wavelength of one contraction of the heart to the next contraction is the distance of the peaks. On the left, we can see another depiction of this. Here we have a frequency counter, which goes this red dot, which goes up and down. The speed of this dot gives the frequency, and as you can see, wavelength, Wellenlänge, is the distance to the same elongation, meaning point, peak in the wave. There's one more important relation between wavelength and frequency of an oscillation. This is the phase velocity, c equals lambda times f, and this would be the velocity with which this blue wave propagates to the right. We have some quantities like the amplitude is the maximal elongation. Yes, it's more of a summary here, and the period duration is 1 divided by the frequency. This is the upper picture shows it looks similar, but the x-axis has a different quantity. So this is a standing wave, and in the upper graph, and in the lower wave we have the time quantity on the x-axis. So wavelength and period depicted in a similar way, but they're not in the same domain. So there is some distinction to make here. I'm not now going to discuss biophysical models, and therefore I need to shortly discuss entropy. This is more or less the second law of thermodynamics, and can be described as heat can't of its own volition transition from a body of lower temperature to a body of higher temperature. or it can be described as a measure of disorder, which is a little bit inaccurate. I must say it's more like a measure of possibilities to arrange a certain state. But it's, this explanation is maybe a little bit harder to understand. If you look at the picture on the right, you see if something is well ordered, like on the in the picture with little entropy, there's only one arrangement to make to realize this ensemble. Whilst on the right, there can be a lot of different ways to get something like this. Not exactly like this, but something like this. For example, if we think of this blue and red squares as gases which are separated at the beginning of the experiment, and we open up between them, we would expect to, after some time has evolved, to have something like on the right side. And this is more or less the meaning of entropy. So it usually the system evolves to an equilibrium. This was the classical thermodynamic, mostly done with ideal gas conceptions. And this is an irreversible process. So you would not expect that from the right a state would evolve into the left state of the depiction. Now, living organisms are not enclosed systems and don't exist with such equilibrium states. So we have to extend the definition of entropy. And this was done in one way with cybernetics, which Moderator defined as control and communication in the animal and machine. It was studied with similarities, developed in studying the similarities between the human brain and computers. One can say that the behavior of a system results from the ratio of signal reception to signal processing. Disturbances of the flow of information are disintegrating factors. It describes organisms as complex systems with self-organization and combining autopoietic, so to say, self-creating structures and interlinked cybernetic regulatory mechanisms. What I mean with this is homeostasis, for example, feedback, self-organization. Homeostasis is, for example, a thermostat who controls a certain value and gives feedback to the system to regulate itself. In this sense, life is cybernetic. There is a more precise definition of this regulatory processes and why they evolve. And this is was brought up by Ilya Prigozhin, and he called this dissipative structures. These are self-organizing, dynamic ordered structures in nonlinear systems far from thermodynamic equilibrium. These systems need negative entropy exchange with the environment in order to maintain a non-thermodynamic equilibrium. They're not in the thermodynamic equilibrium of the same temperature everywhere. There's equilibrium of all system quantities, but they are far from this expected equilibrium. And the reason for this is they have a local entropy minimum at farther away from the thermodynamic one, which if they get energy from outside to maintain this equilibrium, it's less entropy consuming than returning to the thermodynamic equilibrium. By the way, thermodynamic equilibrium for life means death, because there is no this dissolves everything into atoms, more or less. So in order to maintain life, we need energy and mass transfer with the environment to maintain the structure. This means these are open systems. This doesn't is not restricted to organisms, but it also can be observed in natural phenomena like hurricanes, the honeycomb pattern in heated liquids, which I will discuss as an example of this effect, because it's very simple. It's called the Bénard effect, but also galaxy formations and organisms. And this, as I said before, by reaching a transition point, this can experience a break of symmetry. This means there's a local minimum of entropy, and within this minimum, there's a new non-thermodynamic equilibrium, where a formation of stationary order dissipative structures can occur, and this is called the phase transition. By supplying suitable non-chaotic energy, dissipative structures can adopt highly specific ordered states and form spatial-temporal correlations, and particles exhibit long-range correlations. Now I'm discussing a simple example for this to make it clear. There's it's a everyday example in a way, because if you hit a pot on a oven and you heat it from the bottom up, and you heat the thermodynamic equilibrium one temperature water, uniformly the same temperature. You heat it away from the thermodynamic equilibrium, and this temperature gradient causes a difference in density in the water. So hot water rises up, cold water sinks down, and a convection of cellular structure emerges, which gives order to the system in a way. It's not in the same way, but similar. Also, what's happening, for example, in the sun, we have also this cellular structure, convection cells. Yes, and it needs energy to be maintained. If you turn up the heat, this order dissolves. In a more complex way, this is also happens also within humans or all life in some way. We absorb energy from the outside for food and respiration and produce negative entropy, which we use for self-ordering. The net effect on entropy is still positive, because we destroy something to order ourselves. So in sum, the entropy is still positive. It's therefore possible to support self-organization of the organism to self-correcting control processes in case of intact regulatory circuits and unhindered flow of information, instead of controlling it with external signals. Now shortly discussing bioenergetic medicine. This bioenergetic medicine signifies a group of medical procedures which use energy fields in diagnostic and therapy. Usually, this encompasses the use of electromagnetic fields, sound waves, mechanical vibrations, and light waves. As I discussed in the cybernetics part, organisms are subjected to regulatory and control mechanisms which interact on different levels. These levels possess a hierarchic arrangement, and illness in an organism is preceded on higher levels by proceedings whose result is the illness itself. To explain what I mean a bit clear, I give the instance of different time domains for the regulatory systems. For example, there's relative slow regulation of the immune response via blood perfusion. A faster response would be the nerve systems with combination of electrical impulses and secretion of transmitters. And for example, another example is biophotonics. There's an ultra-weak photon emission of cells. This was discovered by Fritz Albert Bopp, and these are attributed to communication between cells. The temporal sequence is as follows. We have a preliminary stage where illness is not yet detectable, and then early in the full stage where it has begun structurally manifest, and then at some point has fully manifested. So the sooner we can detect these changes, the better it is to therapy it. Generally speaking, control levels are more subtle than effect levels. And we now use analysis of heart rate variability, biophotons on skin impedance measurements to detect these preliminary stages of a pathological process. So we can treat it early, so it can be treated early on. And the biophysical methods in this way substitute organ analysis and chemical pharmacological measurements, or offer an alternative to them. I'm now discussing two measurement methods on the one, and the heart rate variability. This is defined as the variation of time between two heartbeats. Two heartbeats are the time interval between the beginning of two contractions of the ventricle. It's called the air interval. It's about 200 to 800 milliseconds, and corresponds to the period duration or heart rate. And the variation of this heartbeats is the heart rate variability. For example, at this symbolic electrocardiogram on the right side, you can see that the peaks are not always at the same distance. They vary a little bit. So one can measure this variation by spectral analysis or Fourier analysis. Because it's not sinusoidal, but it has a characteristic frequency in healthy humans. It's seen as the ability of an organism to adapt the heart rate to physical and mental stress. For example, here we see a spectral analysis of the heart rate variability. For example, we have here parts which are low frequency, 0.04 to 0.15 hertz, This is corresponds to the baroreflex. This means blood pressure changes. If the blood pressure rises, the heart rate goes down, and vice versa. And the high frequency part from 0.5 to 0.4 hertz is the respiratory sinus arrhythmia. This is corresponds to respiration. So if we inhale, the heartbeat goes up. If we exhale, the heartbeat goes down. And this is represents at the time the parasympathetic and sympathetic nervous system. So it can be used to see if analyzed to see if the human body adopts well or is impaired in some way in its ability to adopt. Then we have skin impedance measurements. These are measurements with micro-electrode arrays on the skin. We have here the case that we just take the measurements on the upper layer of the skin. Roughly modeled, we can say one can say that the skin has ohmic and capacitive resistance, whereas it has impedance, whereas the body resistance, as a deeper in the body, if for example you would measure from one arm to the leg, there would be other ohmic resistance within this measurement. But in a surface measurement, you can neglect this ohmic resistance and just concentrate on the capacitive resistance. This is done with macro electrode arrays. These are electrodes. In this case, 128 electrodes, which measure the currents, which corresponds to a voltage change caused by a shift of the charge carrier ions. So you make if neurons or muscle cells are excited, the ionic currents flow through the membranes, and this changes charge potential inside and outside the cell. And during the recording, the electrodes convert the potential change caused by the ion flow. The currents in microamperes are measured, which are taken from the skin surface by randomized pins, electrodes. And the current status of this dissipative electromagnetic structure is an expression of the regulatory capacity of the organism under study. These results of this measurement then compared to normal and log normal distributions seen here. Is the probability density functions of log normal seen on the right and normal distribution on the left. So several values of mean value and standard derivation. This is because of the log normal Verteilung represents the ideal response of well-adapted biological systems, and the normal Verteilung means random chaotic reaction to an impulse. This is due to the Weber-Fechner law, which states that the human body has a logarithmic increase in neural activity. For example, like the decibel in hearing. So If it's a normal distribution, it is just random reaction, not no aimed reaction of the organism. The degree of agreement with the measured distribution represents the ability of the self-regulation of the organism in this way. So thank you for your attention. This was the webinar.
Thank you very much, Jan. Maybe you can show us your face one last time before you leave us. So this is the time now to ask Mr. Senekowitsch questions. You can use the chat function for this. And again, a very big thank you for the insights Mr. Senekowitsch gave us today, the theoretical background. We're going to have a follow-up seminar next week on November 27th at 3 p.m. Central European Time. So make sure you're registered for that. As well, we did a recording today of this session. So this recording will be sent to you in
2 weeks.
Probably 2 weeks, in a short matter of time. So you will be able to follow up the series of these webinars. I do not see any questions yet. You always have the possibility to send us questions afterward as well. And thank you again very much, Jan, having you here today, giving us these insights. What is for sure that you will be able to have this video. So the presentation is involved in this recording video that we did today. So I say goodbye and thank you to everybody to join us today, and stay healthy, stay well, and have a good time.